Hi, welcome to this video where I'll talk about our paper titled Can We Break Symmetry with Little O-M Communication? I am Shreyas Pai. This is joint work with Gopal Pandurangan from University of Houston, Sriram Pemaraju from the University of Iowa, and Peter Robinson from CityU Hong Kong. And this work was done while I was a PhD student at the University of Iowa. We consider the fundamental question of message complexity of symmetry breaking problems in the CONGEST model. Examples of symmetry breaking problems include maximal independent set, delta plus 1 coloring, maximal matching, ruling sets, vertex cover, etc. In this talk, we will mainly consider delta plus 1 coloring. Symmetry breaking problems have been extensively studied for over 3 decades. But this study has mainly been from a round complexity perspective. In fact, all known distributed algorithms for delta plus 1 coloring still use omega of m messages. We want to ask, is this omega of m messages an inherent barrier? And if not, can we design algorithms using little o m messages? Such questions have been studied well for global problems. In particular, our book et al. Show an omega m message complexity lower bound for global problems like broadcast for the wide class of comparison-based algorithms. In comparison-based algorithms, operations on IDs are restricted to be just comparisons. Many CONGEST algorithms are comparison-based, but some are not, and good examples include the Cole-Wishkin algorithm and the MST algorithm of King, Putten, and Thorup. Surprisingly, using the KKT result, we can show that broadcast can be solved with little o m messages using randomization on the IDs. And this beats the omega m lower bound of our book et al. By using non-comparison based operations. We try to get similar results for delta plus 1 coloring in this work. In particular, we show omega m message complexity lower bound for comparison based algorithms, and we show an O tilde n to the 1.5 message non-comparison based algorithm running in O tilde d plus square root of n rounds. Here the O tilde notation hides polylogarithmic factors in n. We work in the standard CONGEST model, which is a synchronous message passing model, where the nodes can send O of log n bit messages per neighbor per round. We are given a graph G as the communication network, and the goal is to solve a problem like delta plus 1 coloring on the communication network G. The focus is on designing algorithms that are round efficient, but message complexity is also an important measure. Message complexity is defined as the total number of messages sent by all nodes in the network. This is considered, in the worst case, over all input graphs. The reason why one should consider message complexity is that communication is costly and consumes a lot of energy. So it makes sense to minimize the total amount of messages sent by the algorithm. Message-efficient CONGEST algorithms also lead to round-efficient algorithms in many all-to-all communication models like congested clique, K-machine, and MPC. Initial knowledge is an important factor when we consider message complexity. In particular, we can consider the KT0 model, where the nodes just know their own ID, and the KT1 model, where the nodes also know the IDs of their neighbors. Getting omega m message complexity lower bounds in the KT0 CONGEST model is relatively straightforward using edge crossing techniques. What is more challenging is to prove message lower bounds in the KT1 CONGEST model. In fact, one cannot even show omega m lower bounds in the KT1 CONGEST model because there is an O tilde n message algorithm in KT1 CONGEST that can solve any problem. And this algorithm is outlined in a paper by Robinson. The algorithm is basically compute a spanning tree using a construction like King, Kuten, and Thuru, and then use time encoding to send input graph information up the tree. This algorithm requires exponential rounds, so we can get really good message complexity at the cost of very bad round complexity. So the two questions that we ask can be modified a little bit by asking, is omega m messages an inherent barrier for fast algorithms or a special class of algorithms like comparison-based algorithms? And if not, can we design algorithms using little o(m) messages with few rounds? So now we will look at our comparison-based lower bounds. We will first describe how the edge crossing technique works to get a lower bound for broadcast. So consider a graph G and an edge E and assume that no message is sent through E. We consider a copy of the graph G called G prime and also consider the corresponding edge E prime. Note that no message is sent through E prime as well. Now we take the two edges E and E prime and replace them with these dashed edges. And through an inductive argument, we can show that because no messages were sent through E and E prime, the states of all the vertices in this graph is the same as the state of all the vertices in this new graph. Therefore, if one tries to solve broadcast in this new graph, there can be no information sent from G through G prime. So solving broadcast is impossible. This leads to a contradiction, and our assumption that no message was sent through E must be wrong, which implies that a message has to be sent through the edge E. Using the edge crossing technique in KT1 congest is a bit tricky because the nodes know the IDs of their neighbors. In particular, the vertex I here knows the ID of its neighbor J. And when we cross the edges, the vertex I now knows the ID of its neighbor J prime. Since the IDs are unique, the initial states of I in the two graphs will be different, so no inductive argument will work. To combat this, Auerbach et al. Consider the model of comparison-based KT1 congest algorithms, where the local computations on IDs are restricted to be just comparisons. This is done by having the IDs be stored in special variables on which you can only perform comparisons. In the KT1 congest model, the nodes get the IDs of their neighbors for free, so it makes a lot of sense to restrict operations on these IDs. Now, one might ask, why not just use random IDs? In particular, why not just ignore the original IDs that have a comparison restriction and generate new IDs uniformly at random? There are no restrictions on these new IDs, so we are golden. But notice that if we generate these new IDs, then the nodes cannot know the new IDs of their neighbors using few messages. So if we ignore the original IDs, we are effectively in the KT0 model. And we already know omega m lower bounds for general algorithms in KT0. For example, we know such a lower bound for MIS as well. So the broadcast lower bound of Auerbach et al. Proceeds as follows. The nodes in G are assigned even IDs. In particular, the node I is assigned the ID 2i and the node J is assigned the ID 2j. The corresponding nodes in G prime are also assigned the same IDs, but they are shifted by 1 so that we have unique IDs in the entire graph. Now, when we consider the crossed edges, the vertex I has a neighbor with ID 2j plus 1 whereas initially it had a neighbor with ID 2j. So the relative ordering of the IDs in the initial information of I has not changed. And this allows us to get to do a more clever inductive argument and get an omega m lower bound for broadcast. When we try to extend this lower bound technique to coloring, we immediately run into a problem because in the crossed instance, the valid coloring of the original instance is still valid. In particular, we don't see any monochromatic edges. So to combat this, we need to consider the following crossing. Instead of the crossed edges, we put these parallel edges. And now we see that we immediately get monochromatic edges, but the initial information of the nodes might be different. Therefore, we somehow want to switch the IDs of I prime and J prime so that the initial information of all the vertices is still the same. Now, if we switch the IDs of I prime and J prime, we risk also switching the colors of I prime and J prime, and we'll be back in the original situation. So the crux of the construction needs to be that we should be able to switch the IDs of I prime and J prime without switching their output colors. And we obtain this as follows. The graph G has three parts, capital X, capital Y, and capital Z, each having t vertices. And the copy G prime has three corresponding parts, X prime, Y prime, and Z prime. The nodes in X have even IDs in 0 to 2t. The nodes in Y have even IDs in the range 10t to 12t, and the nodes in Z have even IDs in the range 20t to 22t. We consider a triple X, Y, Z, and the edge E is labeled as YZ. And for the corresponding triple X prime, Y prime, Z prime, the edge E prime is X prime, Y prime. And the edges E and E prime are crossed as shown. Initially, each node in G prime has the same ID as the corresponding node in G, and we shift the IDs in X prime to get ID of X prime equal to ID of Y plus 1. And we shift the IDs in Y prime to get ID of Y prime equal to ID of Z plus 1. Moreover, we shift the IDs in Z prime by a large multiple of t. The gaps in the IDs between capital X, capital Y, and capital Z ensure that our shifts do not overlap. Now, since ID of Y prime is ID of Z plus 1, the neighbor of Y in the original instance and the neighbor of Y in the new instance have adjacent IDs, and the same is true for all the four vertices Y, Z, X prime, and Y prime. This allows us to use the same inductive proof of our book et al. To show that the behavior of vertices in both instances is the same. Now, since we just shifted the IDs, we did not change the relative ordering. Therefore, the output coloring in both G and G prime will be the same. And therefore, we get a monochromatic edge in the crossed instance. Now, the crux of final argument is that if there is an little om message algorithm, we can find many such edges E and E prime through which no message is sent, and we can perform this proof, this inductive proof, on such edges E and E prime. This allows us to prove an omega m or an omega n squared message complexity lower bound for delta plus 1 coloring. We just saw a sketch of a deterministic lower bound, but using Yau's lemma, we can extend the deterministic lower bound to randomized Monte Carlo algorithms with constant failure probability. Therefore, the result we get is that the message complexity of delta plus 1 coloring in the comparison-based KT1 congest model is omega of n squared. We also show comparison-based lower bounds for other problems. In particular, we show that the message complexity of MIS in the KT1 comparison-based congest model is omega of n squared. This is a powerful technique, and we were able to extend it to problems like non-trivial vertex coloring, edge coloring, maximal matching, approximate vertex cover, and dominating set. And these results are still unpublished. Now let's move on to the non-comparison based upper bound. We show a coloring upper bound where we present an O tilde n to the 1.5 message complexity algorithm in KT1 congest. And this algorithm is non-comparison based and runs in O tilde d plus square root of n rounds. Therefore, the result we get is that the message complexity of delta plus 1 coloring in the non-comparison based KT1 congest model is O tilde n to the 1.5. So the coloring upper bound is based on a constant round congested clique algorithm of Chang et al. In this algorithm, they randomly partition the vertices into V1 through V square root of delta and a leftover set L. And we also randomly partition the color palettes into C1 through C square root of delta. Now each partition Vi has the property that the graph induced by the vertices in Vi has O of n edges with high probability. For each vertex in the set Vi, we restrict the palette of that vertex to be the colors in Ci. And we get the property that the restricted palettes of all the vertices is at least the maximum degree in the induced graph plus 1 with high probability. Now the leftover set is something that we recursively solve the problem on again. Now a node needs to compute its partition Vi and its color palette Ci without too much communication. It needs to know which of its neighbors are in the induced graph of Vi to color the partitions efficiently. Let us assume that the nodes already know this information, and we will show in the next few slides how they obtain this information. Now, if the nodes know all this information, then we can just run a coloring algorithm on each Vi, which takes O tilde n rounds, O tilde n messages, and O of log n rounds. And since the color palettes of each of the Vi's are disjoint, we can run all of these in parallel, and we use O tilde n square root delta messages and O of log n rounds. Another thing to note is that the number of recursive calls is constant, so when we recurse on the set L, we only add a constant factor to the round and message complexity. What we show is that if we have O of log squared n shared random bits, the nodes can compute the partitions based on hash values of their IDs. Hashing the IDs is a non-comparison operation, and the hash function plus the KT1 information gives us the partitions of neighbors without any further communications. The O of log squared n random bits suffice because we show that the randomized analysis works with limited independence. Now actually sharing the random bits is done using few messages by using a sparse spanning subgraph called a Danner. A Danner is a spanning subgraph with O of O tilde n to the 1 plus delta edges that can be computed in O tilde d plus n to the 1 minus delta rounds and O tilde d plus n to the 1 plus delta messages. This holds for any parameter delta between 0 and 1. If we put delta equals half, we can use the danner to broadcast the log squared n random bits using O tilde n to the 1.5 messages. By looking at this coloring algorithm, we in fact get a general theme for designing message efficient algorithms in the non-comparison KT1 congest model. The idea is to use a small amount of shared random bits and KT1 information to get the initial random choices of the neighbors for free. Then we use a danner to share these random bits efficiently. Knowing the initial random choices of all the nodes allows us to save messages for coloring. But for a problem like MIS, we still don't know how to save messages this way. So let me now summarize the results for delta plus 1 coloring. We show an omega n squared message complexity lower bound for comparison based algorithms, and we show an O tilde n to the 1.5 message non-comparison based algorithm running in O tilde d plus square root n rounds. We also saw that we can show comparison based lower bounds for other problems. In particular, we can show omega n squared message complexity lower bound for MIS, and we can also extend it to several problems like non-trivial vertex coloring, edge coloring, maximal matching, and so on. And these results are still unpublished, but the MIS result is in the paper. We also show some additional results in the paper. In particular, we show that the message complexity of delta plus 1 coloring and MIS in KT row congest model is omega of n. In KT row, we have initial information of neighbors up to row hops. We also show that the message complexity of 1 plus epsilon delta coloring in non-comparison based KT1 congest model is O tilde n. And we show that the message complexity of MIS in the comparison based KT2 congest model is O tilde n to the 1.5. We can put it all together in this table where we show KT1 upper and lower bounds for delta plus 1 coloring and MIS in the comparison and non-comparison setting. Note that we only are able to show matching upper and lower bounds in the comparison-based setting. In the non-comparison based setting, there is still a gap between the best known upper bounds and lower bounds. In KT2, in fact, in all the settings, there is a gap between the upper and lower bounds. And filling these gaps for each of these settings is an interesting open problem in and of itself. Out of all these open problems, I would like to highlight two, which is what is the message complexity of MIS in the KT1 congest model for non-comparison based protocols. In this case, the best upper bound is O tilde of m, whereas the best lower bound is omega of m. And second, can we show an n to the 1.5 message complexity lower bound for MIS in the comparison based KT2 congest model? In this case, the best upper bound we show is O tilde n to the 1.5, but the best lower bound we can get is omega of n. And with this, I thank you, and I hope to see you in PODC 2021.